In this series of videos, I'll be showing you how to find the maximum temperature of a flame based on an inlet stream of fuel and air. So here we have our flame, and into the bottom of it, we'll have our fuel, which is natural gas, and airflow, which will provide oxygen for the reaction. So the composition of the air is oxygen and nitrogen in a 21 to 79 mole ratio. For our fuel, which is natural gas, it'll be composed of methane, ethane, and propane. And in the we're given in the problem the percents of each of these hydrocarbons. So methane is 94% of the fuel, ethane is 4%, and propane is 1%. So we are going to assume that this flame is adiabatic, which means there are no heat losses to the surroundings. So this simplifies the problem a little bit, and it'll allow us to find the temperature because the enthalpy of the inlet stream, which is the natural gas and the air, will be equal to the enthalpy of the flame. And we can use that to find the maximum temperature of this flame. So we're also going to assume that the change in potential energy of the inlet stream or the change in potential energy of the system is 0. That way we don't have to account for the height change as the air travels to the top of the Bunsen burner. So we're going to start with getting at the mole ratios of our natural gas components and components of air. So we're going to start by balancing a combustion reaction. I'll start with methane. So in a combustion reaction, it always reacts with oxygen to burn, and the products are carbon dioxide and water. So now we need to balance this equation. The moles of carbon in the hydrocarbon are always equal to the moles of carbon dioxide. In this case, it's just 1. Then we need to balance the hydrogens in the hydrocarbon. So we have 4 on this side, and we need 2 moles of water to account for that many hydrogens. And now we need to balance the oxygens. So there's a total of 4 on the right hand side. So we need 2 moles of oxygen to have a total of 4 moles of O. And since we also have nitrogen coming in with the air, we have to account for that. Although it doesn't react, it's still in a reaction. So it is the same moles of oxygen times the 79 to 21 ratio of air. So this just kind of carries through the reaction since it's not reacting with anything. So we will add it on the product side as well. So now I can do the same thing for ethane, which is C2H6. We'll have a certain amount of moles of oxygen, carbon dioxide, and water as products. And we'll also have our moles of nitrogen. So again, start balancing the carbons. There's 2 in the hydrocarbon, so we have 2 moles of CO2 on the right side. There's a total of 6 hydrogens in the hydrocarbon, so we need 3 moles of water to balance that out. And then there's a total of 4 plus 3 oxygen on the right hand side, so we need a total of 7 on the left hand side. And we'll write that with a coefficient of 7/2. And then we have the moles of nitrogen that come in with the oxygen, which would just be 7/2 times the ratio of 79/21. And then again, our last reaction will be propane, which is C3H8. We'll have oxygen, the nitrogen that comes in, and then the products of CO2, H2O, and then the nitrogen that carries through the reaction. So again, we'll start balancing the carbons. There's 3, so we'll have 3 moles of CO2. Balance the hydrogens, there's a total of 8. So we have 4 moles of water, and then we can balance the oxygen, which is a total of 10 on both sides. And then we can account for our nitrogen using the ratio. So now we're going to have to adjust these reactions to account for the excess air that's going into the flame. So we have a total of 20% excess air. So I'll just do this for the first reaction since it's the same for the next 2. We'll still have our moles of methane going in, but now we have to account for the excess oxygen that goes in. So that'll be 1 plus our excess, which is 20%, times our oxygen, and we have 2 moles from the reaction. So that'll be the amount of moles of oxygen that goes into the flame. And then the same thing for the nitrogen. And that accounts for the extra moles of nitrogen. So then on our product sign, since all of the oxygen won't react, we'll have oxygen as a product. So we'll still have our 1 mole of carbon dioxide, 2 moles of water. We'll also have 0.2 times the mole ratio of oxygen. In this case, it was 2. And then again, we'll just have the amount of nitrogen that went through with the reaction. So now I'm going to switch over to Python and code this into our code so we can start to model the temperature of this flame. All right, so now that we have the stoichiometric ratios of our fuel reactions, we can go ahead and put those ratios into our code. So what I have here, I've imported CHE tools, and I've set it to the first path so we can use it. I've also imported NumPy because we'll use a lot of NumPy arrays in this code and a few other NumPy functions. And I've also imported SciPy root, which we'll use to find the temperature in the last part of this video series. So what I'm going to start with is the composition of our fuel. So we are going to make a NumPy array, which will represent the moles of methane, which is 0.95, our moles of ethane, which is 0.04, and the moles of propane, which, as you can see, I'm just using the percent of our fuel composition. So this represents the moles of methane, ethane, and propane in our fuel mixture. Now we need to get at the amount of carbons and hydrogens in each of these hydrocarbons, so we can use them to find out the moles of oxygen and nitrogen that'll go into a reaction with air. So I'll just call this the fuel CH. And I'll create another NumPy array. The first set of values is going to be for methane, so there's 1 carbon and 4 hydrogens. Next, for ethane, there's 2 carbons and 6 hydrogens. And then for propane, there's 3 carbons and 8 hydrogens. So now to get at basically the average amount of carbon and hydrogen that go in with our fuel stream, we're going to multiply this value by the amount of carbons in methane, add it to the amount of carbons in propane, which will be this 0.04 times 2, and add that to the amount of carbons coming in with the propane, which would just be the 1% times the amount of carbons, and it'll be the same deal with the hydrogens. So to do this, we will do a matrix multiplication. So we'll matrix multiply our moles of fuel times the stoichiometry of the chemical makeup, and that'll give us the moles of carbon and moles of hydrogen coming in with the reaction. So we can go ahead and unpack that. And now we can use these values to figure out the rest of the stoichiometry for this for burning our fuel. So the moles of carbon dioxide will always be equal to the moles of carbon coming in. The moles of water will be equal to half the moles of hydrogens coming in with the hydrocarbon, since there's 2 moles of hydrogen in a water molecule. So A times H2. And then for our moles of oxygen, it will be the moles of carbon dioxide plus half the moles of water, since there's only one oxygen molecule in a water molecule. We'll have half of that, since the chemical makeup of pure oxygen is O2. And the last piece we need to get at is the moles of nitrogen. And this will just be equal to the ratio of oxygen to nitrogen in air, which is 79/21 times our moles of oxygen. So there we go. Now we're going to go back and account for the excess air that's coming in with the reaction. So in our problem, we have 20% excess air, so that changes the amount of oxygen we'll have coming in, which will just be 1 plus the amount of excess. And then in this equation, it changes the moles of oxygen, which will also change the moles of nitrogen. So now we can use this to get at the chemical makeup of our stream going in and the stream coming out of the Bunsen burner. So our stream in will be, we're going to concatenate the moles of fuel with the moles of oxygen and nitrogen. So it'll be our moles of fuel, and we'll add in a matrix of the moles of oxygen and the moles of nitrogen. And then there is no carbon dioxide going into the reaction, and there's also no water going into the reaction. So now if we take a look at this, we have the moles of methane, ethane, propane, oxygen, nitrogen, and there's no carbon dioxide or water going into the burner. So now we'll do the same thing, but we'll define the chemical makeup of the stream coming out. So we'll do this as a numpy array. There is no propane, ethane, or methane coming out because it's all reacted and burned and created the flame. We will have the excess amount of oxygen that's going that won't be used up in the reaction, and then we will have the moles of nitrogen that kind of go along with the rest of the reaction. And then we'll also have the moles of carbon dioxide. Yeah, the moles of carbon dioxide and the moles of water that are generated during the reaction. So now if we take a look at this array, we have the moles of methane, ethane, propane, water, nitrogen, carbon dioxide, and water that is coming out of our the Bunsen burner. So now I'll use this in the later videos to calculate the total enthalpy change for the flame, and then we'll be able to get at the maximum temperature of the flame.